All right, we're continuing with section 1.3 in the geometry textbook. So we're talking about, at the start of this section, we looked at the meaning of a good definition and what a postulate is, an axiom. Postulates and axioms are the same thing, mathematical systems. And so now in the second half of this section, what we're going to do is actually go over some of the initial postulates and definitions that we're going to start with in geometry. Now that we understand what exactly a postulate is and a good definition is, and the role that these play in this mathematical system. All right, so recall that a postulate is a statement that is assumed to be true, but you don't have to prove it. So postulate 1, through two distinct points, there's exactly one line. All right, so you can think about, again, that might seem to be common sense, and it is. That's why, I guess to me, that's what makes a good postulate, is that it's just common sense. Everyone can agree on that. But technically, we haven't proven it because, what exactly is a line? What is space around us? You could go forever trying to prove things, and so we're just going to make this statement here. And another reason you can think about why this is going to be a postulate is because if you try to define it, remember a good definition is that one feature is that you can put it into a category, a larger category that everyone understands. Well, you can't really do that here. You can't. What category would you put a line in? A figure? But what's a figure? You can't. There's a point where it's kind of ridiculous to try and define things around you. It just is what it is. Right now, I'm talking into a microphone. Oh, what's a microphone? What does it mean? What does life even mean? Well, okay, no, but we're all alive. We all observe things around us, and there's common facts we can all agree on. Those are like postulates that we're not going to prove. You're watching this video right now. I don't need to prove that. That just is what it is. That's the idea of a postulate, okay? So postulate 1 is sometimes stated in the form, 2 points determine a line. Yeah, so if you have 2 points in space, then that makes that defines one unique line. 2 points in space, there's exactly one line, not more than you can't have more than a different line going through the same 2 points in space. That's the idea. So here, C and D determine exactly one and only one line. Line CD, of course, postulate 1 also implies that there's a unique line segment determined by 2 distinct points. Yep. Used as endpoints. Recall figure 1.31, in which points A and B determine line segment AB. Yep. In geometry, the reference numbers used with postulates, as in postulate 1, need not be memorized. Okay, so they're saying the fact that this is postulate 1 doesn't mean anything. The fact that it's the first postulate. Okay, in figure 1.33, how many distinct lines can be drawn through point A? So just one point, well, there's an infinite number of lines. And that makes sense because if it takes 2 points, distinct points, to define a line, then if you're dealing with 1 point, then it would be, there's an infinite number of lines you can put going through that 1 point. Okay, both points A and B at the same time. Well, based on postulate 1, there's only there's going to be one unique line going through points A and B. I can't draw another line that also goes through points A and B, and that's just the consequence of lines are straight. I have to kind of bend the line. If I went through B to get to A, I'd have to bend the line, and that's not what our informal definition of a line says. Okay, what about all points A, B, and C at the same time? Okay, that's a good question. So, all at the same time, there's no line because C is not collinear with A and B. They're all separated. Now, what exactly does that mean? We haven't talked about yet, but I mean, we could just do this. What exactly does collinear mean? How you determine something is collinear? But that's if you can draw one line going through all points. Well, one unique, let's look at it this way. If 2 points define one unique line, okay? Yeah, here's a good way to break this down. 2 points we know define one unique line. That's what the postulate 1 says. So I'm going to go ahead and draw that line through point A and B. That's close enough. Is that the exact line? That's close enough. Okay, well, if that's the only line that goes through points A and B, then if C is collinear with A and B, then C would be on that line, or maybe it'd be very close, and you could say that maybe I just didn't draw the line correctly. But so it should be either on the line or very, very close for us to say that, okay, they could be collinear. Well, this is not even close to being on the line. So C is, you can't draw, it's not collinear with A and B. I could draw a line through A and C, but then, okay, is B collinear there? Well, no. So no line contains all 3 points. All right, recall from section 1.2 that the symbol for line segment AB, named by its endpoints, is segment AB. Omission of the bar means length of the segment. Okay, the symbols are summarized in table 1.3. So, yeah, it was, you had a line with the 2 arrows indicating it extended infinitely in all directions. Omit the arrows, now you have a line segment. That's like a figure. And now omit the bar itself, and now you have that represents a number. A ruler is used to measure the length of a line segment, such as segment AB. This length may be represented by AB or BA. The order of A and B is not important. However, AB must be a positive number. All right, so the measure of any line segment is a unique positive number. Here's the ruler postulate. And why is this intuitive? Why is this just an assumption we can make, and this kind of common sense is the way I would look at postulates? Well, because how could you take an actual measurement of something in relation to something in space? So right now we're talking about lines, but anything in space, and it be negative. I mean, that doesn't, it could be, I'm not saying you can't have negative lengths, like negative velocities, but that's just talking about, okay, you're going in one direction versus the other direction. As far as physical space around us, if we're talking in complete general, the length of a line segment is not going to be negative. So that's like the absence of a line. The line extends into another dimension. Maybe that would make sense in 500 years or something. But right now, no. If you measure the length of a line segment with a ruler, it's going to be a positive number, and actually not just positive number, but a unique positive number. And what they're saying there is that someone could take a measurement of a line with a ruler, a line segment, and then someone else could take a measurement of a line segment with a ruler and get 2 different measurements. But that's just the measurement the measurement uncertainty. In general, they're saying a line segment has one length. Makes no sense that the line segment can have 2 different lengths at the same time, is what that's saying. We wish to call attention to the term unique and to the general notion of uniqueness. Okay, yeah, here we go. About uniqueness. The ruler postulate implies the following. There exists a number measure for each line segment. Only one measure is permissible. Yeah, that's not, they're not saying that if 2 people they measure the line, they get one gets 11.1 millimeters, the other gets 11.2, that's not permissible. That's not what they're talking about. They're saying that it's, like when it comes to functions, here's a good example of a function, from algebra, the idea you can't have the same input corresponding to separate, the same input corresponding to separate outputs. Someone can't say, okay, this line measures 11 millimeters, and someone else say, no, no, this line measures 5 millimeters. You're taking 2 different measurements. This line has one and only one length. That's the idea of unique. Characteristics 1 and 2 are both necessary for uniqueness. Other phrases that may replace the term unique include one and only one, exactly one and no more than one. Right. Now, something that's not necessarily unique is, like an equation with multiple solutions or infinite number of solutions. You can input different, you can apply different inputs and it will satisfy the equation. The solution is not unique. There's not one and only one solution. A more accurate claim that the commonly heard statement, the shortest distance between 2 points is a straight line, is found in the following definition. Okay, so now they're going to make a definition about and this makes intuitive sense. You could start off with an intuitive statement here that the shortest distance between 2 points is a straight line, but they're able to define this with an actual definition. Ideally, we wouldn't need postulates in a perfect world. I could actually make definitions out of everything. That would be ideal. And so, I'm not a mathematician, but my guess would be that you want to have as few postulates as possible. Anything that you can make a definition, go ahead and make it a definition. It's only when there's no way to, put it into a larger category. You can't make a formal definition that you say, okay, well, we have to make this a postulate. So, all right, the distance between 2 points A and B is the length of the line segment AB that joins the 2 points. Okay, so the distance between 2 points A and B, we're stating here's distance, and something that's related to 2 points in space, A and B. There's a distance between 2 points in space, A and B. Okay, it's a length, so that's a dimension, a space dimension of the line segment that joins the 2 points. So what kind of length is it? This is the larger category. It's this dimension of space, this distance between 2 points. It's this dimension, the space dimension, not a time dimension or a temperature dimension. It's a space dimension. Okay, that's the category. But what distinguishes it from other space dimensions? Well, it's the length of the line segment that joins the 2 points. Not an arc, not in some sort of a curved path or anything. It's the line segment. Okay, now how is this reversible? Well, okay, you would say the length of the line segment between 2 points is the distance between the 2 points. Yeah, both of those make sense. So now how does this imply the shortest distance between 2 points is a straight line? I mean, I don't know how it implies it. That's kind of a definition, because we didn't have to define the distance between 2 points to be a straight line. We could define it to be a curve, but I think that's more of a that sounds like more of a postulate. The sense that since a line is perfectly straight, then how could any other distance but the line segment distance between 2 points be the shortest distance? It would have to be the shortest. I think it's common sense to think about the shortest distance between 2 points is there's a straight shot from one point to the other with no, perfectly straight line laser shot. That's a postulate, a common sense postulate, and we define that to be the distance between the 2 points. But that's a definition, though. We didn't have to. Again, we didn't have to say that. You could say the distance between 2 points is the arc of radius 3, center here, going from that point to the other point. Well, you could say that. Now, why would you do that? I don't know why you define it that way, but you could. So, but that's not the distance. We think about it as the shortest distance between 2 points being the line segment connecting those 2 points, the length of that line segment. All right, as we saw in section 1.2, there's a relationship between the lengths of the line segments determined in figure 1.34. Here, okay, this relationship is stated in the third postulate. The title and meaning of the postulate are equally important. Okay, the title segment addition postulate will be cited frequently in later sections. So, all right, if X is a point of segment AB and A-X-B, which we saw was A-X-B was describing collinear points, where X is between A and B on the same line or line segment. So X is a point of segment AB, A-X-B, X is between A and B, all collinear, then AX plus XB is equal to AB. Okay, so the segment addition postulate, let's read this again. If you have a point X that's on segment AB, and so since AB are the endpoints, you can state that as A-X-B. These 3 points are collinear. X is between A and B. Then the magnitude of AX, the length of AX plus the length of XB is going to be equal to the length of AB. The segment addition postulate. This is common sense, but still, we're formally stating all of this. And it's a postulate here because you can think about for yourself how it's too abstract to try and define this. You can't do a proper definition of the segment addition idea. All right, in figure 1.34, find AB if AX is equal to 7.32 and XB is equal to 6.19. Just add these two up. If AX is equal to 2x plus 3 and XB is equal to 3x minus 7, just add those two up. And we'll work example problems like this in the next video as well. So, all right. Okay, definition. Congruent line segments are two line segments that have the same length. Okay, so we talked about the meaning of congruence in the previous videos, and when it comes to line segments, they're congruent if they have the same length. Now, this doesn't mean that you can say two triangles are congruent if they have the same, what are you going to say, the same area? Well, no. So this is just a special case where, so we know congruence is the parallel to equals. Equals is dealing with two numbers. Two numbers have the same, quantity. Congruence is applying to figures. That it's the idea that you have these two geometrical figures and they could be oriented completely differently in 3D space, but if you can reorient one or both of them however you want, flip them, whatever, but don't change their size, don't scale them, just reorient them. And when reorienting them, you can put them on top of one another, and it's a perfect match. Then they're said to be congruent. And you can think about that. It's the case when it comes to line segments that if any two line segments have the same length, they're going to be congruent because you can put them anywhere in 3D space, orient however you want. But if they have the same length, well, then you can bring them together, flip them, whatever, and put them on top of one another, and they're going to match perfectly. So it just happens to be the case that with line segments, it's a simple, congruence is a simple case of if they have the same length, they're congruent. But now when it comes to other shapes, it's not that simple. Again, you can't say if two triangles have the same area inside the triangle, they're congruent. No. In general, geometric figures that can be made to coincide, fit perfectly on top of one or the other, are said to be congruent. The congruent symbol is a combination of the symbol, this squiggly line, which means that the figures have the same shape, and equals, which means the corresponding parts of the figures are the same measure. Okay, so it's same shape and measure. So it's not just, yes, if you have two triangles that are congruent, then they're going to have the same area. That's true. So the measures the angle measures and everything are going to line up, but they also have to have the same shape. So it's more than just equals. It only works out that way where it's kind of the measures are the same with line segments because it's a relatively simple figure. In figure 1.35, AB is congruent to CD, segment AB congruent to segment CD, but segment AB is not congruent to segment EF, meaning that segment AB and EF are not congruent. Does it appear that CD is congruent to EF? No. CD is not congruent to EF, AB is not congruent to EF, but AB and CD are congruent. In the U.S. system of measures, 1 foot is equal to 12 inches. If AB is equal to 2.5 feet and CD is equal to 2 feet, 6 inches, are AB and CD congruent? Yes, because 2 feet, 6 inches is just 2.5 feet. How many feet is 6 inches? It's a half of a foot. So 2 feet plus a half of a foot is 2.5 feet. Definition. The midpoint of a line segment is the point that separates the line segment into two congruent parts. So the midpoint of a line segment states the term is the point. So it's a point. We know what a point is. Okay, what kind of point? Just any point in space? Well, no, it's not. What is unique about this point? It separates that line segment that we're talking about into two congruent parts. So two parts that have equal length. All right, in figure 1.36, if AM and B are collinear and AM is congruent to MB, then M is the midpoint of AB. All right, so this might seem trivial and obvious, but we're building this mathematical system. If point M is such that it separates AB into two where the length of AM is equal to the length of MB, then M is the midpoint of AB. Now, I'm assuming they're going to ask, well, is M the midpoint of CD? It doesn't look like it, because M is collinear with C and D. It's on line segment CD, but MC is not, the length of MC is not equal to the length of MD. So no, it's not the midpoint of CD, but it is the midpoint of AB. Okay. Also, if AM is congruent to MB, then CD is described as a bisector of AB. Okay. So that's just another way of describing this. CD, line segment CD bisects line segment AB. So remember, we can have a bisector of a line, a bisector of an angle. So CD bisects AB, but AB does not bisect CD. If M is the midpoint of segment AB in figure 1.36, we can draw any of these conclusions. AM is equal to MB. MB is equal to 1/2 AB. Yeah, exactly. There's multiple ways to write this. That AB is 2 times AM, or AB is 2 times MB. All right, given M is the midpoint of segment EF, not shown, EM is equal to 3x plus 9, and MF is equal to x plus 17. Find X, EM, and MF. Okay, so you can do, okay, M is the midpoint of EF, so you can say that, let's see, 2 times, and we could do 3x plus 9 is equal to what? EM plus MF. There's multiple ways to go to solve this, right? You could say 2 times 3x plus 9, or 2 times x plus 17, whatever you want, or you could use any of these relations, is equal to and then EM plus MF. So let's see, 6x plus 18 is equal to 4x plus 16. Subtract 4x from both sides. Subtract 18 from both sides. Did I do that right? 2 times 3x plus 9. Oh, no. I didn't. 17 plus 9 is 26. Okay, subtract 4x from both sides. Subtract 18 from both sides. X is equal to 4. So there's x, and then EM is just going to be 3x, 3 times 4, 12 plus 9, 21, and then 4 plus 7 is 20. Yeah, they're both equal. So 21 is EM and MF. In geometry, the word union is used to describe the joining or combining of two figures or sets of points. So yeah, we talked about this in algebra, but in set notation, where we are, we're kind of viewing figures this way as well in postulates and definitions from the perspective of set notation. So, thinking about any of the ways we've used set notation so far, the idea is union is you have two sets, or I guess multiple sets, more than two, but it's everything in set A and everything in set B. So all of this is a union, and you write that as A union B. Now, intersection is just where they intersect. That's A intersection B. And then we saw like a subset, if you had, we saw earlier in chapter or section 1, if B is a subset of A, you would do B is a subset of A. All right, definition. Ray AB denoted by, and they've got just a one-sided arrow here, is the union of segment AB and all points X on AB such that B is between A and X. All right, so that's a lot there. What are they saying here? You've got AB, there's a ray AB, the union of segment AB and all points X on line AB such that B is between A and X. So, okay, let's think about what they're so we've got segment let's start with a line here. Okay, we can come here. Here's line AB. So it's the union of all points X on line AB. So we can think about every single point on line AB, okay? But there's obviously some restriction to this. So it's the union of segment AB, okay, and all points on line AB such that B is between A and X. Okay, so so X would be, we can think about X is out here. B is always between A and X. So it's the union. So all points on segment AB, and all points X such that B is between A and X. So any point to the right of B. So the union of all points on segment AB and any point to the right of AB, which is an infinite number of points, but nothing else. So we're not including these points over here. You wouldn't have, okay, is this X as well? Well, no, because B isn't between A and X in that case. So that's not included in these X points. So there it is. There's the definition of ray AB. And if you say ray BA, it's just, you just kind of flip that definition. Not flip it, but reorient the letters. That would be, so ray BA would be the union of segment AB and all points X on line AB such that such that A is between B and X. So that's a good example. You see how, this might seem that why so complicated? Why make this so? It's just an array. It's obvious. Well, no, that's not the way definitions work. You need to build this system. You need these formal definitions. This is part of what makes the math bulletproof. All right. Opposite rays are two rays with a common endpoint. Also, the union of opposite rays is a straight line. Yeah, so you can't just say, to say opposite rays, you can't just say that. The only thing you can't just say that they have a common endpoint, because I could say, okay, here's an endpoint, here's ray, AB, and here's ray AC. So A, B, A, C. Okay, are those opposite rays? Well, no. They also, the union of opposite rays is a straight line. If I took the union of AB and AC, I wouldn't have a straight line. If I took the union of AB and AC here, I've got a straight line. So it's those two criteria. And for your 1.39a, ray BA and ray BC are opposite rays. Yeah. Okay, the intersection of two geometric figures is the set of points that the two figures have in common. In everyday life, the intersection of Bradley Avenue and Neal Street is part of the roadway. Yeah, so I don't know if I like that example too much. Well, no, that's not bad. So yeah, technically an intersection is where that is pretty interesting. And if you think about the precise meaning of an intersection, that's when you're standing in the middle of an intersection, you're standing on two streets at the same time. You are. Because which street are you on? You don't. You're on both. Okay, and so what would if I come back here, what would the intersection of ray AB and BC be? Ray AB and ray AC, ray AC and ray AB. What would that be? Point A. That's it. 1 point. That's the only place where you're on this ray and this ray at the same time. All right. And in set notation, again, it's like you would say, if you have two sets, like if this was ray AB and this was ray AC, then their intersection would be point A, and you're calling that, AB intersection AC, at least in set notation. And if you're doing set notation, that's how you do it. All right. Postulate 4, if two lines intersect, they intersect at a point. Okay, that's interesting. They don't intersect at a plane. They intersect at a point. Intersection of two lines, if they intersect at one point. When two lines share two or more points, the lines coincide. In this situation, we say there is only one line. So, yeah, you might say, well, what about, you could have a line that intersects, you could think about it as intersecting at more than one point if we do something like this. Well, in that case, you don't say they intersect. You say they coincide. They're like the same line. So there's only two cases. The lines are either not going to intersect at all, or they're going to lie on top of one another, or they're going to intersect and it's going to be at one point. So if you think about potentially here, there could be two lines lying on top of one another, line AB and line BC, maybe even a third line, line AC. We don't know. There could be three lines here, but we don't say they're intersecting. We say they coincide. They're the same line, whereas these two lines intersect, line L and line M at point P. But now the idea, what if they don't intersect? Then here's another definition. Parallel lines are lines that lie in the same plane but do not intersect. Okay, so this definition here, it's important to note that it includes in the same plane. In the same plane. So if we think about 3D space, there's an infinite number of planes in 3D space. The ZY plane, the XY plane, the XZ plane. That's just three of the main planes, but you can draw planes all over. Okay? But you can think about, though, I could draw two lines in 3D space. I could draw like a line up here, but then I could draw a line kind of below that, like that. Okay, well, those two may never intersect, depending on how I drew them. So, are those considered parallel? No. You need to be able to put them in the same plane. If you can't put them in the same plane, if one plane doesn't contain both the lines, then you don't consider that parallel. It's kind of like planes that are flying over one another. Well, they don't intersect, right? But so does that mean that they're traveling in like parallel directions? Well, no, not really. They're just in different kind of planes in space. They're not flying in parallel. If you have a plane, one flies above and the other flies below it going the other direction, they really kind of, they cross, but they don't crash into each other. That's not parallel paths. Okay, in figure 1.40, suppose that L and N are parallel. In symbols, you do, yes, like L is, you could do like that, parallel. And the intersection of L and N, there is no intersection. The empty set is the empty set. However, L and M are not parallel because they intersect at point A, L and M. And so you can do L is not parallel to M, and the intersection of L and M is point A. They're talking here. So in figure 1.40, L is parallel to N. What is the intersection of N and M? Lines N and M. So N intersects M at point, or B. B, what about the intersection of L and N? L intersecting with N is the empty set. Another undefined term in geometry is plane. A plane is two-dimensional, that is, it has infinite length and infinite width, but has no thickness. So remember the idea of zero-dimensional, one-dimensional. It's what you can measure. If it has a portion that can be measured, at least in terms of space we're talking about, then that's included as a dimension. Well, a plane has no thickness. A point has no, it can't be measured in any direction. Zero-dimensional. A line has a measurement in one direction. A plane can be measured in two directions, but there's no thickness. It's two-dimensional. Except for its limited size, a flat surface such as the top of a table could be used as an example of a plane. But in real life, there's no perfect planes. And we think of a plane, a postulate for a plane is that it's perfectly flat. It's a postulate because, well, what does flat mean? What exactly does flat mean, right? An uppercase letter can be used to name a plane. Because a plane, like a line, is infinite, we can show only a portion of the plane or planes. So yeah, plane is perfectly flat, just like a line is perfectly straight. But what does that mean exactly? We're not going to go into that. But you can draw a plane. You know, we put arrows to indicate that the line goes infinitely in all directions. Plane is the same idea. It extends infinitely in all directions. So you just try and indicate that as best as you can. Okay. A plane is two-dimensional, consists of an infinite number of points, and contains an infinite number of lines. So yeah, a line contains an infinite number of points. And actually, so does a plane that contains an infinite number of points, just like a line. But something else about a plane is that it also contains an infinite number of lines. You could draw an infinite number of lines within the plane. This line isn't contained in the plane, but you can draw an infinite number of lines in a plane. Two distinct points may determine a line. Likewise, exactly three non-collinear points determine a plane. Yeah, so that's interesting as well. If we know that two distinct points in space, not the same points, or define one line, one and only one line. Well, it's the same idea with a plane, but 3 points. You have 3 points will constrain a plane. And then just like how 1 point, you can draw an infinite number of lines through 1 point, well, you can draw an infinite number of planes through a line. So you have a line here. Well, you can draw an infinite number of planes that go through that line, or that contain that line. Just as collinear points lie on the same line, coplanar points lie in the same plane. In figure 1.42, points B, C, D, and E are coplanar, whereas A, B, C, and D are non-coplanar. Yeah, B, C, D, and E are coplanar, but if you include A in that, then it's not going to be coplanar. A is not in the plane. In this book, points shown in figures are generally assumed to be coplanar unless otherwise stated. For instance, points A, B, C, D, and E are coplanar in figure 1.43a, as are points F, G, H, J, and K in figure 1.43b. Yeah, so we're going to be doing a lot of work in planes with triangles, polygons, parallel lines. So it's what they're saying is that for the most part, we're going to be working in planes. And so unless it's clearly stated otherwise, we can assume that we're working in a plane. And if that's the case, then the points are coplanar. For example, we're going to be studying in the second or third chapter properties of parallel lines with transversals going through the lines. So you have parallel lines and transversals, and we're going to be studying the angles relationships here for the entire chapter. Well, we know parallel lines are in the same plane, right? So all the examples are going to be in a plane. So they're not going to need to state every time that, okay, look, all these points are coplanar. It's implied that we're in a plane. Same thing when we're going to do a lot of studying on triangles and polygons. Well, those are all two-dimensional objects. So we're going to be in plane. So all the points we're dealing with are coplanar. So if we're dealing with a non-coplanar points or situation, it's going to be stated explicitly. All right, postulate 5. Through 3 non-collinear points, there's exactly one plane. So yeah, there's that official statement with, they made this statement as a postulate with a line, 2 points define a line. Here's the statement that 3 points define a plane, 3 non-collinear points. On the basis of postulate 5, we can see why a 3-legged table sits evenly, but a 4-legged table would wobble if the legs were of unequal length. That's interesting. All right, space is the set of all possible points. It is 3-dimensional, having qualities of length, width, and depth. When 2 planes intersect in space, their intersection is a line. So yeah, when you think about space, just space around you, just the universe, it's the set of all possible points. Any point that exists that's what space is. It is 3-dimensional. So yeah, there's 3 in space. There's 3. You can make 3 distinct measuring orientations: up, down, left, right, front, back. So three-dimensional, having qualities of length, width, and depth. When two planes intersect in space, their intersection is a line. An opened greeting card suggests this relationship, as does figure 1.44a. This notion gives rise to our next postulate. So yeah, when two planes intersect in space, and it's the same idea when it comes to, we're not talking about like parallel planes or the same plane lying on top of one another. It's like the same idea with lines. If it's just these two non-parallel or not the same plane that intersect, well, two lines intersect at a point, and when it comes to planes, two planes are going to intersect at one unique line, just like lines intersect at one unique point. But planes can be parallel, as shown here, or they can lie on top of one another as well. So postulate 6, if two distinct planes intersect, then their intersection is a line, a unique line. The intersection of two planes is infinite because it is a line. Exactly. But with two lines intersecting, it wasn't infinite. It was one point. So if we come back here, there's the line, right? See that line? And just to note that it's similar to lines, like if you shifted this plane over without changing its orientation, it's still that's a different plane. It's like the idea of you can have a line and it's got a certain slope, and if you just shifted the line without changing its slope, that's a different line though. It's not the same line. It has a different equation and everything. So same idea. Yeah, you can, if you moved this plane here without changing its orientation, well, you might say, well, look, that's a different line that's intersected with it. Well, that's a different plane then. These two planes are unique. So they intersect at one line if they intersect. All right, if two planes do not intersect, then they are parallel. The parallel vertical planes, RNS and figure 1.44b, may remind you of the opposite walls of your classroom. The parallel horizontal planes is like the ceiling and the floor. Yeah. So there's the parallel horizontal planes, and there's the parallel vertical planes. Imagine a plane and 2 points of that plane, say points A and B. Now think of the line containing the 2 points and the relationship of line AB to the plane. Perhaps your conclusion can be summed up as follows. So let's try and think about what they're going to say in this postulate. Imagine a plane and 2 points of that plane, say points A and B. Now think of the line containing the 2 points and their relationship of AB to the plane. So if you have to me what they're about to say is, if you have a plane that contains 2 points, and you think of the line that goes through those 2 points, then that line is, every single point of that line is contained within the plane. So given two distinct points in a plane, the line containing these points also lies in the entire plane. Yeah. Okay, because the uniqueness of the midpoint of a line segment can be justified, we call the following statement a theorem. The proof of the theorem is found in section 2.2. So now we're going to go from this isn't a definition, because this is more of this is an observation we're making from as a result of the definitions and postulates we've come up with so far. So this is something that you can prove and justify. So the uniqueness of the midpoint of a line segment can be justified. So, okay, the theorem is that the midpoint of a line segment is unique. You don't have multiple, you can have multiple planes going through the same line. You cannot have multiple points that correspond to the same midpoint of a line segment. It's one and only 1 point. That's a theorem. If M is the midpoint of segment AB in figure 1.45, then no other point can separate AB into two congruent parts. No other point in space. The proof of this theorem is based on the ruler postulate. M is the point that is located 1/2 AB units from A and from B. The numbering system used to identify theorem 1.31 need not be memorized. However, this theorem number may be used in a later reference. The numbering system works as follows. Yeah, so chapter 1, section 3, and it was the first theorem. All right, so there's the postulates and definitions and one theorem that we're going to start with in this textbook.